Section 1.2, we're going to start looking at patterns. And there's some vocab that we need to talk about before we can because they're going to come up in a lot of our example questions. So let's start there. The first vocabulary word that we're going to look at today is the word conjecture. A conjecture is a statement or a conclusion that has not been proven. You might also think of it kind of like the word hypothesis, right? It's what we typically are saying we believe to be true. We don't know necessarily if it is. A counter example is something that proves a conjecture false. It means the conjecture didn't work. And then there are two types of reasoning, inductive and deductive. Inductive reasoning is the method of making generalizations based on observations or patterns. And deductive reasoning is the use of mathematical axioms, theorems, definitions, or undefined terms assumed to be true and logic for proof. The majority of the reasoning you do is inductive, like in your real life. So, Wednesday. Do you guys remember what the weather was like on Wednesday? It was really beautiful, wasn't it? It's like 70 degrees and there's almost no wind. It was just downright gorgeous on Wednesday. But prior to that, and the last 2 days since that, hasn't really looked quite like that, has it? It's been cool. It's been windy. So if we were looking at generalizations of patterns and we had several days in a row of cool, windy weather, your expectation prior to grabbing your phone and looking to see whether you're true or not is that the next day would be cold and windy, right? And we do that all the time. It's called inductive reasoning. Okay. So we can do that with patterns as well. So when a child looks at a pattern that says triangle, square, triangle, square, triangle, square, they're looking at examples and they guess what happens next. That's an inductive reasoning. They may be right, they may be wrong. Okay, they don't really know for sure, but they're using the pattern to inductively decide what comes next. Deductive reasoning happens mostly within the realm of things where we can create an equation for them. So mathematics. Okay, so for example, let's say, for instance, you had a pattern that went 2, 4, 6, 8, 10, 12. Probably you would say that looks like those are just even numbers, right? We're just using all the even numbers. So talking about what happens next based on what happens before, that's inductive reasoning. Now, if I gave you an equation that says y equals 2x, and I said x is 5, you would tell me y is 10. You just plug that number in. That would be deductive reasoning. You have an equation to start from, and you're using that to know what comes next instead of looking at what came before. Okay? So we're going to do some examples of both of these types of reasoning in a second. A couple more vocabulary words before we get there. Sequences. Sequences are an ordered arrangement of numbers, figures, or objects. So when you start with kids really, really little, it's usually objects. Square, triangle, red, blue, right? They're looking for a pattern and there aren't any numbers involved. I specifically remember little bitty books that I would buy for my kids to do during the summer because I'm that mean mom. You know, the one that says you should still be like trying to learn something during the summer, not letting your brain go to rot. Yeah, and so they would have these pattern recognitions in there when my kids were very young. Okay? And then as we mature and as we continue through school, at some point somebody introduces patterns of numbers like 2, 4, 6, 8, and we talk about the pattern of those. And certainly by the end of second grade that's happening because you're looking at multiplication tables. And that's exactly what multiplication tables are, right? They're really just a pattern, multiples of 3 or multiples of 5 or something like that. A recursive formula is a formula based on the pattern established after one or more consecutive terms are given, with a rule that shows how to get the next term. Okay, so if you have 5, 10, 15, 20, then the pattern is recognizing that you're adding 5 every time. I mean, that's really what you're sort of doing, right? You're adding 5 every time. And so this idea of a rule that shows how to obtain each successive term would be plus 5. I do plus 5. That's my rule. But the rule only works if I know where I am in the pattern, right? If somebody says, well, what's the next term? You have to know the term before to do that. Agreed? I can't just say, I've got a pattern and what's the next term? And you're like, okay, well, the pattern's plus 5, but where did I start? Where did you leave off? You got to know those pieces of information if you're talking about a recursive formula. These terms, this is a funky font. It looks better on your paper. It says nth, and this says general. I think your book uses the phrase general term, and I use the phrase nth term some of the time. So they mean the same thing. So if you hear me say nth term or general term, we're talking the same thing. What they're doing is they're creating an equation based on the pattern, so that if I ask you, okay, I've got the sequence 5, 10, 15, 20, what's the 20th term? You don't have to write all the terms out till you get to 20 to be able to tell me. Does that make sense? There's some convenience in knowing that. I don't have to do as much work if I've got an equation that's the pattern, that actually stands for the pattern and isn't defined by knowing what came before. How many times do I have to do this to get where I'm going to be? So there's two different ways of having sort of a rule or a pattern analysis, and these are those, okay? Recursive and nth or general term. So we're going to look at a couple of different, we're going to look in depth at a couple of different types of sequences, and then we're going to look more cursory at a few others after that. The first type of sequence we're going to look at is called arithmetic. An arithmetic sequence is a sequence in which each successive term is obtained from the previous term by addition of a fixed number. That's actually the only one I've talked about so far, right? 5, 10, 15, 20, we add 5. The number that we add every time is called a fixed number. Now it's important for you to realize that you could be adding negative numbers. So the sequence could be going down, so it sort of looks like you're subtracting. But just remember that subtraction is just adding negatives. So a fixed number could be positive or negative. All right? So if the sequence went 20, 15, 10, 5, it's still arithmetic. You're just adding negative 5 every time instead. So far, so good? Okay. I think we have one more definition, and then we're going to do some examples. The other sequence that we're going to look pretty in-depth at is called a geometric sequence. And there's some reason why it's called geometric that does involve geometry. We're not going to define it quite like that. But this is a sequence in which each successive term is obtained from the previous term by the multiplication of a fixed number. All right, so these are harder to go further along with, but let's say we do it. 2, 4, 8, 16, 32, 64. What am I doing every time? You're doubling it. You're multiplying by 2. That's a geometric sequence. The common ratio is the number that you're using to multiply by. So in my example, what was my common ratio? 2. Now, again, it's important to realize that your common ratio doesn't have to be positive. It could be negative. It could also be a fraction. Like I could multiply by 1/2 every time. So it sort of looks like the numbers are being divided by 2. That's possible as well, okay? So it doesn't have to actually be a whole number we're talking about here. Most of the sequences will, but there are a few examples in your book that might not, okay? So just be prepared for that. Okay, we're going to do an example. Oh, I'm sorry. There's one more type of theory, sequence that we're going to talk about briefly, and then before we get to our examples. Fibonacci sequences. Okay, just out of curiosity, show of hands, who's heard of Fibonacci before? I'm not going to ask you what it is, just who's heard of it. Okay, 4 or 5 of you. So a Fibonacci sequence is a non-arithmetic and non-geometric sequence that follows a different pattern, and it is very common in nature. So I'm going to write out the first few terms of the Fibonacci sequence. Those of you who said, I've heard of Fibonacci before, keep quiet for a second and see if everybody can find what pattern's being done. Okay, because this one takes a little bit more doing than just adding a number or subtracting a number every time. So let me write out the first few terms. Okay, so what I want you to try to do, this is inductive reasoning, right? Because I'm not giving you a formula. So I want you to try and see if you can figure out what the next number should be. If you know it already, you can write it down, but don't share it with anybody. If you don't know it, see if you can think about it. Okay, turn to a neighbor and compare. See if you got the same thing. If you both didn't get it, it's okay. We're going to do it all together. But see if you agree or if you can explain, if you do know, or pretty sure you have it right, if you can explain why you think your answer, what your answer is. I think about 3 people all at once said, oh. Okay, so when I did my research as a graduate student for my dissertation, the big giant paper you write at the end, and if you come to me and you tell me you have to write a 3-page paper and you're feeling stressed, I might not have a lot of compassion because it was a 175-page paper. So it's been a long time, though. I mean, I don't want to do it again, don't get me wrong. But one of the subjects that I did my research on, his definition of mathematics was the study of patterns. So what you're doing right now is mathematics. You're studying patterns, okay? So what do we think the next term is? 34. Okay, so we're speculating that it is 34. All right, so I heard lots of you describing it to other people, so I'll summarize what you're saying. The way that you get the next terms is you take the 2 numbers before and you add them together to get it. So, for example, 8 plus 13 would be 21, so 21 is the next term. If we were to do this again, we would take 21 and 34, and we would get what? 55. Okay? So this is the Fibonacci sequence. We're not going to do a lot with it, but I do want you to realize that not every sequence is arithmetic or geometric. Okay? It just isn't. This is just one example of another one out there, and it is really common in nature. This sort of seems like an odd place to put this, but we're going to need it in a minute, so I want to make sure that we've discussed it. A to a power n. If n is a natural number, and we haven't really talked about natural numbers, but they're the counting ones, 1, 2, 3, 4, 5. Those are natural numbers, okay? So if n is one of those counting numbers and you have a to the n power, then a to the n is a times a times a times a, all that, n times. If n is 0 and a is not 0, then we say that a to the n is 1. In other words, this is telling you that a to the 0 is 1. And for those of you who've taken proportional and statistical reasoning, we actually prove why that's true there. It's not just a fact that I'm telling you to do, and there's no reasoning behind that. It's just not encompassed in this particular class, okay? So those are 2 facts that we need to know in order to take a look at our formula, or not formulas, but our sequences next. Okay, you ready to do an actual example? Okay. Here's our first example of the day for real. List the next 3 terms in the sequence. That's the first thing we're going to do. Second, we're going to identify if the sequence is arithmetic, geometric, or neither. And then step 3, we will do together. We will find what the nth or the general term is. That's the hardest part of these. So I'd like for you to take a look at sequence A and sequence B and do parts 1 and 2. You should be able to do both of these parts for these 2 sequences. Okay? So take a second, figure out what are the next 3 terms, or what is the pattern, and then what does that make the next 3 terms? And then is it sequence arithmetic, geometric, or neither? When you and someone near you is finished, compare what you have, and then we'll all compare together. Okay, chat with somebody near you. Turn to somebody near you. I see a lot of you stopped writing, so I think you're finished. See if you agree. If you don't, figure out why you disagree. All right, someone from the back of the room over here, what did you get for your next 3 terms on A?
We got 13, 16.
Okay, does everyone agree? Excellent. Okay, so let's go for the middle of the room. One of you guys 3 up front. What did you get for, is this arithmetic or geometric? It is arithmetic, I agree. We'll come back to the general term part in a minute. Okay, over here on this side of the room. Someone sort of here in the middle. What did you get for your next 3 terms on part B?
48, 96, and 192.
Okay, does everyone agree? Excellent. And then, is it arithmetic or geometric? One of you 3. What'd you get? Geometric, I agree. Okay, is everybody good so far? Nice. All right, so what we want to do now is to find a way of expressing an equation, like an equation that tells you what this pattern is. And again, the reason for doing that is, what if I ask you now, what is the 100th term? Right? This is like, this is what I would do if I were Gauss's teacher, back in the problem I gave you last time, right? That'd just be mean if I didn't give you any tool to find it faster than just writing all 100 terms out. So I want to show you how you can create a general term. So the first thing I want to ask you is on part A. It's arithmetic, which means you added something every time. What did you add? 3. That piece of information is really important for the equation we're going to create. Do you remember what that 3 is called? There was a vocabulary definition for it. Fixed number. Sometimes it's also called a common difference. Okay? It's the number you add every time. So this is the fixed number that you're adding. Okay, so we're going to take that number and think for a moment with me. Okay, ignore the 1, 4, 7, 10 that I have up there for a moment, okay? Think with me about another list that you know that adds 3 every single time. What list do you know that does that? Say that louder.
3, 6, 9, 12.
And what are those commonly known as? The multiples of 3, or your multiplication table of 3s, right? Okay, so somewhere along the way, in 2nd or 3rd grade, somebody told you, okay, yes, I know you can add lots of 3s together, but there's a shortcut, and it's called multiplication. And you learned the shortcut, and life got easier. I mean, right? You did. I mean, you didn't like learning the multiplication tables, but once you got it, it made life a lot easier if you were adding together a whole bunch of 3s. Okay? So instead of expressing this as addition, we're going to express it as multiplication. 3 times n. Now, if n is 1, what do I get? 3. If n is 2, what do I get? 6. If n is 3, what do I get? 9. So legitimately, 3n gives me my multiplication tables of 3s, right? I mean, that's what it gives me. Now, this sequence adds 3 every time, but it's not exactly the multiplication tables of 3, right? Where does it start? It starts at 1 instead of 3. So how far off am I on my starting point? I'm off by 2. If it helps you, another thing you could do is you could actually compare it that way. If I were writing down the multiplication tables of 3s, 3, 6, 9, 12, and so on, you can look at them. How far away am I? Well, I just need to subtract 2 and then I'd be on target. And you can check to make sure you're right. So let's check maybe the first 3 terms. If n is equal to 1 and I take 3 times 1 minus 2, what do I get? 1. If n is equal to 2 and I take 3 times 2 minus 2, what do I get? I get 4. If n is equal to 3 and I take 3 times 3 minus 2, what do I get? I get 7. This is the sequence I was given, right? So this is my general term. And it always works that way for addition, for arithmetic sequences. You can always create the term this way. I hate to mention it, but somebody's going to look in the book and they're going to come after me later and they're going to be like, why didn't you teach us this other way? There's another way to do this, okay? I could give you an equation that tells you how to find all these pieces every single time. I'm not a real big fan of that because the whole point of this section is supposed to be figuring out what you're doing by looking at patterns. So this is why I teach it this way, okay? There is an equation in your book. But the likelihood that I tell you go memorize that equation and 2 years from now you have any idea what that equation is probably 0. And if I can teach you how to think about it, I think you stand a better chance at reasoning through it in the future. Okay? Let's look at geometric. All right. You guys told me that it's geometric, which means you multiply by something to get the next term. So what do we multiply by to get successive terms on this? 2 times 2. Okay, middle school is probably where it was, maybe late elementary. Like the 3rd grade teacher that says, yes, you can add 3 together a whole bunch of times and I'm going to teach you a shortcut. You had a middle school teacher probably who said, yes, you can multiply 2's together a whole bunch of times, but I want to give you a shortcut. Do you remember what the shortcut is for multiplying a number together multiple times? Squaring, exponents, right? Exponents. And that's actually why, whoops, that definition on the bottom where I said it feels a little bit awkward to be placed in the middle of what we're talking about comes from. Okay, it's an exponent. So adding something together multiple times is multiplication. Multiplying something together multiple times is exponents. So let's take a look at how we create this exponent. Here's what we do. We take the number that we're multiplying lots of times. Do you remember what that was called? I had a name for it before. It's a common ratio. It's a common ratio. The number you multiply multiple times. It's also a fixed number, but fixed just means it doesn't change. It's the common ratio, okay? So we take that common ratio and we raise it to the power of n minus 1. And let me tell you why we do n minus 1. What happens if I put the number 1 into this portion of the equation so far? What are you going to get for your exponent? 0. Everybody good so far? 0 in the exponent. What is 2 to the 0? 1. So no matter what my common ratio is, by doing the number raised to the n minus 1, the first value is always going to be 2 to the 0, whatever to the 0 is going to be 1. So we're always going to get a sort of an initial value of something, we'll call it a, to the 0 when we do this. That's why we're doing it. But our sequence doesn't actually start at 1, right? What does it start at? 3. So here's the cool thing. You just multiply this by 3. So we're going to check it out. That is to say, how did it work? Or does it even work? So if n is equal to 1, we have 3 times 2 to the 1 minus 1. Well, 1 minus 1 is 0. 2 to the 0 is 1. And 1 times 3 is 3. Was that my first term? It was. Let's try a couple more. N equal 2. If I take 3 to the 2, 3 times 2 to the 2 minus 1. Start with the exponent. What's 2 minus 1? 1. 2 to the 1 is 2. And 3 times 2 is 6. That was my next term. Because what we really got here is we really got 3 times 2. We really had 3 times 1 here, right? That's what we really had. Let's try n equal to 3 and check that one out. So if we do 3 times 2 to the 3 minus 1. What's 3 minus 1? 2. 2 squared is 4, and 4 times 3 is 12. Is that my next term?
Yes.
It is. And the reason it worked is because what I really had was 3 times 2 times 2. Because that's what 2 squared is. And the next one would be 3 times 2 times 2 times 2. Because that's what 2 cubed is. So the pattern in multiplying by 3 happens because of that exponent being involved. So my general term here is 3 times 2 to the n minus 1. Okay, so now I'm going to pause for a minute, flip back if you need to. I want you to decide, this reasoning in this problem, was this inductive reasoning or deductive reasoning? If you don't remember what the difference was, look back. What do we think? It's inductive. Inductive means I have patterns and I'm making a generalization about it. In fact, that's exactly what I did. I made a general term out of it, right? So this is inductive reasoning. All right, let's look at example 2. In example 2, we're going to start with an equation. It says, using the nth term given, find the first 5 terms of the sequence, and then identify if the sequence is arithmetic, geometric, or neither. So in a very real way, we're going to be doing this stuff we did over here with n equal to 1 equals 2 for those patterns that we've got, okay? And we're going to do it for the first 5 terms. So I'll get you started on the first one. You always start with 1. So you do n equal to 1. So we have 5 times 1 plus 6. That would give me 11. You would have multiplied the 5 and the 1, not add them. That's okay. N equal to 2. 5 times 2 plus 6. 16. N equal to 3. 5 times 3 plus 6. 21. N equal to 4. 5 times 4 plus 6. What is it? 26. And if we do 5, you probably don't even have to actually do it. You probably see a pattern. What's this number going to be? 31. So thinking in terms of recursive relationships, what's happening? How do I get from 11 to 16 to 21 to 26 to 31? What's going on? I'm adding. I'm adding how many? 5. Which means, is this sequence arithmetic, geometric, or neither? Arithmetic. Okay? So this one is arithmetic. If we were asked, we could even say that the common difference, that is the number I'm adding every time, is positive 5. Right? Yeah. Now, think about the equation itself. Why, looking at this equation, could I know, even without writing the terms down, that this is arithmetic? Any ideas? There's no power, so that's a good thing already, right? It doesn't look like the geometric one already, so it's definitely not geometric. What else do you notice? Yeah, there's something that's multiplied by n, and then there's something that's added or subtracted at the end. It's got that same image, right? It looks like this type of an equation or expression. That's what it looks like. All right, let's try the next one. I'm going to let you do this one. Find n equal to 1 up to n equal to 5. And find your terms. What'd you get for the first term? 0. I'm not going to write my steps out. I wrote the values, but we got 0. What do we get for n equal to 2? 3. What happened for n equal to 3? It was 8. How about n equal to 4? 15. And n equal to 5? 24. Now, did anybody recognize a pattern that looks like arithmetic or geometric on this one? Do you add the same number every time? Do you multiply by the same number every time? No. So this one is actually neither. It doesn't follow either of those specific patterns. However, it is a pattern, right? What would happen if you just took away the 1 part, the minus 1? Well, you have all the square numbers, right? I mean, n squared. That's a pattern. I want to come back to this pattern here in a minute. I want to show you one more thing with it. But before I do, is this inductive or deductive reasoning? It's deductive. Deductive means you have an equation to start with, and then you create the patterns. Okay? So this is deductive reasoning. All right, so what I want to end today with, I want to talk about this sequence. Okay, so this is neither here nor there on your notes, but it actually applies to some of your homework questions. Sometimes they're going to give you a pattern. You're going to recognize that it's something, but it's not arithmetic and it's not geometric, and they want you to know what's next. And maybe you don't recognize readily what's next. So I want to show you how you can use the information to give you what's next. So we're going to write down that sequence here. 0, 3, 8. What was next? 15 and 24. Thank you. What I'd like to do is I'd like to do an analysis of what happens when we add. Like, what would I have to add to get to the next term? For example, what would I have to add to 0 to get to 3? I'd have to add 3. What would I have to add to 3 to get 8? 5. What would I have to add to 8 to get 15? 7. And what would I have to add to 15, to get 24? 9. Okay, look at the numbers I created. 3, 5, 7, 9. Is there a pattern there? Yes, there is. In fact, if we look at the pattern one more time and do the same thing, how do you get from 3 to 5? You add 2. How do you get from 5 to 7? You add 2, and how do you get from 7 to 9? You add 2. So this line right here is called first differences. And they don't match. And because they don't match, it's not arithmetic. However, in our scenario on this one, the second differences do. And actually, that's why we had an x squared or an n squared as part of our equation in this problem, is because the second differences would match. Now, normally you're just going to start out with the pattern. You're not going to have the equation to start with, but that's the relationship that exists. It's squared because it has the common second differences. If it were cubed, it would have common third differences, okay? So I'm not going to start with this and ask you to create a general term. That won't happen. But there are some examples in your book when you do get to the homework and group work where we will start with a pattern that's not arithmetic, it's not geometric, but you can do first differences, and you could do second differences, and you could do third differences, and at some point you will see what the pattern is. So just looking at these differences, we should be able to figure out what our next term is. If adding 9 was my last step on the sequence I was given, what would I have to add next? 11. Could I add 24 and 11? Well, of course I could. And I would get that the next term was 35. And is the next term 35 for that sequence? If n equals 6, what do you get? 35. Cool, right? Yeah.